familiar with this picture by now. I've removed Peter Higgs because now we're interested in what might lie beyond Peter Higgs. And you can see sort of subliminally on the skyline there maybe a few indications of some possible new physics beyond the standard model. Yesterday my talk was largely concerned with listing the parameters, the constants of the standard model, and not saying very much about where they come from. This time I will say a little bit about where they might come from, although without any very definite provable ideas. And I must confess also that I couldn't restrain myself from trampling a little bit on Paddy's ground by saying a little bit about what happened yesterday, and what that might mean for fundamental constants. So in the standard model we have these three different gauge groups, each of which has its own coupling constant, except, as I remind you, those coupling constants are in fact not constant. They all vary, but we have that technically under control. There's also another parameter that I didn't describe, which characterizes CP violation in the strong interactions. For some reason, that is essentially zero. It has to be smaller than about 10 to the minus 9 or 10 to the minus 10. And there's a whole literature on why that might be the case, and I won't say anything about it. Then we have, if you remember from my pullover yesterday, the third line of the T-shirt. That had to do with the mechanism for giving masses to the fundamental fermions. So of course, those masses are fundamental constants, but there are also the mixing angles between them, and there is also a CP violating phase. Then finally we come to the Higgs sector. So you remember our sort of double well potential. Well, actually it's a Mexican hat because it's rotationally symmetric. So that has two parameters, one mu, which tells you that the center is unstable, and one lambda, which tells you that the potential goes up at infinity. Remember that, the potential has to go up at infinity, because that's going to be something that comes back later on in the lecture. So I get 19 parameters. What would be the agenda for trying to make sense of these constants and maybe reduce them? So obviously there's the program of unification, grand unified theories, but we would like to have a theory of flavor which links together all these constants in the middle there. This, as I already said yesterday, is somewhere where I think there's no idea that commands consensus. And in my talk today, I'm just going to add to the confusion by saying there's actually a whole bunch more parameters that we should worry about. And then, sitting at the bottom here, we have the Higgs sector. And this is one where theorists have given a lot of thought. They've come up with a lot of models. Unfortunately, I think the net result of all that has been to decrease the number of parameters there by about minus 100. And I'll discuss that later. What I'm going to do in the course of this talk is to sort of go through those various different sectors from the bottom up. I guess that sort of temperamentally I'm a sort of bottom-up sort of a guy, although I have been known to go top-down on occasion. But anyway, in this talk I'm going to go bottom-up. So we have this wonderful particle that's just been discovered. It's a completely new kind of particle. We've never seen an apparently elementary scalar particle before. And this gives us theorists all sorts of interesting problems to work on, and also experimentalists. And there's a lot of discussion in the particle physics community. Maybe the next step should be to explore this Higgs boson in more detail. This will of course be done with the LHC, and there's an extensive program planned of upgrades of the LHC, which will certainly be able to reduce the uncertainties in the properties of this particle and maybe determine the related fundamental constants more accurately. Beyond that, ideas are circulating, if that's quite the right word, for a possible next generation collider, which might be a linear collider. There's various ideas about that. Or it might indeed be a circular E plus E minus collider. And there are other ideas also on the market, although I think linear and circular colliders are the ones that are sort of leading the field at the moment. My own personal point of view is that it's premature to put all our eggs in the Higgs factory basket until we've seen what the LHC produces over the next 2 or 3 years, because it's going to operate at higher energy with higher collision rate, and there may be a whole bunch more particles that will emerge, maybe supersymmetric particles, and a whole bunch more fundamental constants that we will want to determine and understand. I mentioned yesterday that there is thinking at CERN about possibly digging a bigger tunnel, which at the moment is called a future circular collider. Following the example of ESO yesterday, maybe we should call it the extremely large hadron collider. So I will put that to the CERN management. Anyway, that sort of small blue ring up there is what the experiments are currently being done in. And that orange thing is just a sort of schematic drawing of what the possible location of this future circular E plus E minus collider might be. This is an illustration of the sort of accuracy of the measurements that you could make. So I showed a picture rather like that yesterday, but based on current data. This is what you could conceivably do with such a machine. So you're determining, for example, whether the Higgs couplings are really proportional to the mass with an accuracy of about 1 per mil. And similarly, or even better, for the overall scale of those couplings. Of course, this machine doesn't only do Higgs physics, and I don't have time to do justice to all the other gazillions of particles that you produce. You produce lots of Z particles, lots of W particles, lots of top quarks. With those top quarks, for example, you can measure the mass of the top with an accuracy which is better than 100 MeV. And I'll come back to the importance of measuring the top quark mass a little bit later on. This is an illustration of how possible future projects could measure the properties of the Higgs boson more accurately than is the case at the moment. So the green bars represent what you could do at the LHC. An interesting point here is that the dashed green bars are what would be possible if we theorists don't do a better job than what we're doing at the moment in terms of calculating standard model processes. The solid green bar is what the experimentalists would be able to do if we theorists put in a decent amount of effort. So I like to show this slide just to emphasize to my theoretical colleagues that we've got to put our calculating boots on. Then you've got a linear collider, ILC, that's the blue one, and then this circular collider that I've been talking about, that's the red one. So there is a program possible of measuring the properties of this particle, as I said, at the percent or conceivably even the per mil level.
The dots would be just as bad for the other machines, would they?
No.
They wouldn't?
No, because the other machines are electron-positron colliders, and they're technically, the calculations are under much better control. Your problem with a hadron collider is you've got strong interactions in there, and the strong coupling is, well, it's getting weaker, but it's still much stronger than the weak coupling. So there are little dashed error bars, but they're very small. So what could you do with such measurements? Well, I'm going to be talking later on about supersymmetry, so maybe this slide is a little bit premature. But what you see on the right-hand side there is the uncertainties attainable with different accelerators in specific signals for the Higgs boson. So photon-photon, ZZ-WW, glue-glue. And then you can make out little symbols there. Those little symbols are typical supersymmetric model predictions. So in a supersymmetric model, typically you don't get precisely the same prediction as in the standard model. And the little offsets there represent that difference. But just to emphasize again that we theorists have to do a better job, the green bar at the bottom there represents the current theoretical uncertainty in calculating the properties of the Higgs boson. So again, we theorists are going to have to do a lot better if we want to measure the fundamental properties of the Higgs boson. At least my reading of this is that if you really want to distinguish a standard model Higgs boson from, say, a supersymmetric one, then you're going to want to go to the best possible machine, which would be this circular machine called here TLEP. So here I've emphasized the Higgs, but I just want to remind you of one comment that I made yesterday. One of the fundamental constants in the standard model is taken to be the mass of the Z boson, which is currently known with an accuracy of 2 MeV, which is 2 × 10⁻⁵. With such a machine, you can measure it in principle at the level of 100 keV, so a factor of 20 better, 1 part in a million. And that again is going to require a tremendous effort, in particular to understand where the French trains go. This circular E plus E minus collider that I mentioned is just part of what I would describe as a vision for particle physics in the 21st century. No, once you've conned the countries of the world into digging a big tunnel, then of course you could put other things in it, and in particular you could put in a large proton-proton collider, which we call VHE-LHC, but again by analogy with ESO we should call it the E-LHC for extremely large hadron collider. And the effort is just now starting to develop the physics case for such a complex. That's what I wanted to say about the Higgs sector, but I will return to supersymmetry a little bit later on. I think it's fair to say that with the continuing overwhelming success of the standard model, there is a sort of countercurrent among theoretical physicists, or maybe experimental physicists, maybe both, to say, well, maybe there is nothing beyond the standard model. And I would like to caution the community against hubris, and I'm going to trot out a few examples. Michelson, 1894, 3 years before the discovery of the electron. The more important fundamental laws and facts of physical science have all been discovered. Kelvin, 1900, 5 years before the discovery of the photon, or the postulation of the photon by Einstein. There's nothing new to be discovered in physics now. All that remains is more and more precise measurement. Our very own, or your very own, Stephen Hawking is the end in sight for theoretical physics. Well, I'm not quite sure what horizon he's working to, but it's over my horizon. So particularly relevant to this discussion of this large circular collider that I was just discussing is another one which historically is much earlier. So many centuries after creation, it is unlikely that anyone could find hitherto physical theories of any value. So all of us who write grant applications are familiar with that sort of report back from the referee. So I don't know whether the sort of future circular colliders that currently we're thinking about will receive the same sort of response from the member states of CERN, but if they do, we'll quote Christopher Columbus back at them. That's all very well, but actually is there any evidence at the current time for any physics beyond the standard model? Well, there is. Well, there are pieces of evidence. And one of them is produced by neutrino physics. So a series of experiments that I don't have time to discuss now have shown that the different flavors of neutrino, remember there are 3 different flavors of neutrino, these 3 different flavors of neutrino mix and oscillate amongst themselves. I wouldn't say the only, but certainly far and away the simplest interpretation of those data is that those neutrinos have different masses, that the mass eigenstates are not the same as the weak interaction eigenstates that you produce, for example, in muon decay or beta decay. And under that hypothesis, the mass squared differences, what I call here delta m squared 2,1 and delta m squared 3,2 have been measured. And the mixing angles, the 3 mixing angles, have also been measured. Now, of course, by analogy with what you've already seen for the quarks, there should also be a CP violating phase. And one of the interesting results of the past few months, I might actually have described it as the most exciting result of the last few months before yesterday, was that there is a hint when you put all the different pieces of neutrino data together that maybe the CP violating phase is beginning to emerge. And I'll say something about that on the next slide. The point I want to make here is that you cannot accommodate neutrino masses within the standard model as I wrote down on yesterday, or the Norwegian high school teacher knitted on yesterday's pullover. You need additional parameters, 3 more masses, 3 more angles, 1 more phase, 7 more parameters. And if you did that, that theory would not actually make calculable sense. If you wanted to make a theory which was actually renormalizable and hence calculable, you would actually need, I would say, at least 18 parameters. So almost as many parameters in the neutrino sector as we already have in the standard model. So I just want to flesh out a little bit the remarks that I made about neutrino mixing and also just show you this hint concerning CP violation. So these neutrino oscillations are measured in reactor experiments, accelerator experiments, and also using astrophysical neutrinos, solar neutrinos, and also atmospheric neutrinos. And these enable those 2 mass differences that I mentioned to be measured pretty accurately. And as I showed you, the mixing angles are now also quite well measured. So this is the current information, which is taken from a recent article by Gianluigi Fogli and collaborators. And so top left, you see 1 mass squared difference. Top middle, you see another mass squared difference. Along the bottom, you see 3 mixing angles. And top right, you see this CP violating phase. And the vertical axes in each case are the numbers of standard deviations. So you can see that the likelihood function varies by more than 4 over the range of the CP violating phase delta. So this is not a proof of anything, but it is at least interesting that we're getting now into the if I could dare to say it, the phase of exploring CP in the neutrino sector, which, as I said, is entirely beyond the standard model. So let me now talk about another indication for physics beyond the standard model, which is provided by the Higgs. But you may say, well, yesterday and earlier on this morning, I was at pains to say everything we know about the Higgs is consistent with it being the standard model particle. True, but now let's look at the information in a little bit more detail. So you know that fundamental constants, many of them, are in fact not constant. They evolve as a function of the scale at which you measure them. And that's also true of the quartic self-coupling of the Higgs field, the lambda that's supposed to make the potential go up at large values, if you like, the brim of the Mexican hat. And that lambda is renormalized, well, actually it's self-renormalized, and that just tends to make the thing get bigger still, so that's fine. But there is also a renormalization of that quartic coupling lambda by the top quark. And that is negative, and it's proportional to the top quark mass to the 4th power. So potentially, if you pardon the expression, that negative renormalization could drive the Higgs lambda coupling negative at some scale, and that would actually generate an instability in our current electroweak vacuum. And here from a paper by de Grassi et al., you see a calculation of how that Higgs self-coupling lambda goes down as you increase the energy scale. And you get to about 10 to the 10, 10 to the 13 GeV. The Higgs self-coupling goes negative, and that is a signal of vacuum instability. So as I said, that sets in somewhere around 10 to the 10, 10 to the 13 GeV. Now, that instability could be cured if you postulated supersymmetry, but I'll come to that in a moment. Let me just continue with this argument. So here I have a parameter plane. The horizontal axis is the mass of the Higgs boson. The vertical axis is the mass of the top quark. And there is a large green region where the standard model is completely stable. There's a red region where it's certainly unstable. And there's a yellow region where it's metastable. So that means the vacuum is in principle unstable, but the lifetime is longer than the age of the universe. And in the blow-up on the right-hand side, you see where the data currently places, and that is actually probably in the metastable region. Not in the stable region, but in the metastable region. So that means that if you take that result at face value, all we have to do is wait around for 10 to the 12 years, and our universe will disappear in a puff of dust. Well, perhaps not dust, a big crunch, anyway. This is a little picture of what happens. The Mexican hat brim goes up, and then it is brought down by the top quark renormalization, and we don't know of anything to stop it within the standard model. Now, the conclusion that the current electroweak vacuum is unstable within the standard model is a provisional one, and it depends on uncertainties in, for example, measuring the Higgs mass, measuring the top mass, and measuring the strong coupling strength. This, from a calculation by Butazzo et al., shows you how the uncertainties in those fundamental constants play in to the stability or otherwise of our electroweak vacuum. The largest uncertainty in this is actually the mass of the top quark. I think we now know the mass of the Higgs boson reasonably well. Of course, we'd like to know it a little bit better from the point of view of this argument, but we would really like to know the mass of the top quark better. And you can somehow sort of see this. If you go to that sort of darts board picture on the right-hand side, you'd have to go a long way to the right to get into the stable region. But you don't have to go very far down, changing the mass of the top quark to get into the stable region. So hence the interest in measuring the top quark mass as well as possible. I've given you a couple of indicators that presumably there is physics beyond the standard model. Neutrino masses certainly require physics beyond the third line of yesterday's jumper. And this instability in the electroweak vacuum, if it's confirmed, would also, in my mind, require some physics beyond the standard model. So what else is there? Now I'm going to utter the S word. And I am a believer in supersymmetry, so I've written it in the largest possible font on this slide. Well, there's all sorts of reasons for liking supersymmetry, and I'll mention some of them in a moment. There are sort of traditional ones like naturalness, grand unified theories, which I'll mention in a moment. It could explain dark matter, that would be good. It also, I think, got two additional pieces of experimental support within the last couple of years. One is that supersymmetry correctly predicted the mass of the Higgs boson. It predicted that the Higgs boson should weigh below 130 GeV, which it does. And it also predicted, as you saw a few slides back, that the couplings of the Higgs boson should look very much like those in the standard model. So now I'm going to be quite bullish about supersymmetry. Of course, the crunch will come when the LHC energy is increased and we see whether supersymmetric particles come out of its wazoo or not. Naturalness is a word that is used a lot, and one could have a whole philosophical debate about how strongly one should take the argument. But let me just phrase it in the context of the Higgs mass. Here I've written down two one-loop diagrams that renormalize the Higgs mass. And those diagrams are, each of them, quadratically divergent. So there's a contribution coming from scalars, which is actually the lower of those two lines, and there's one coming from fermions, which is the upper one. Now, because of the well-known fact that fermion loop diagrams have a minus sign, those divergences have opposite signs. And it does not take a rocket scientist or even a field theorist to observe that you could cancel out that leading divergence in the contributions to the Higgs mass squared if you had this particular relationship between the scalar coupling and the fermion coupling. Where perhaps a field theorist would be useful is to point out that that relationship is exactly what happens in supersymmetry, and a field theorist could also prove to you that that cancellation of those quadratic divergences is something that works not only at the one loop level, but if you calculated 964 loops, it would also cancel. So there is some very strong principle at work, and supersymmetry relates boson masses to fermion masses. Fermion masses are protected by chiral symmetry, and that's what gets rid of those quadratic divergences. So what that means is that you don't have to worry about getting ridiculously large corrections to the Higgs mass squared in a supersymmetric theory. You don't have to worry that you might have to adjust the tree level value of the Higgs mass squared so that it cancels out against the loop corrections that you calculate later on so as to give you 0 to 34 decimal places. Supersymmetry, no problem. Now, there's one other feature of supersymmetry that I would like to mention, and that is electroweak symmetry breaking. So you remember that electroweak symmetry breaking happens in the standard model because you've got a potential which is unstable at the origin. Now, it turns out that in supersymmetry you can actually calculate or predict that negative behavior close to the origin. And in fact, it comes back to our old friend, the top quark. In this case, you're happy that it drives that particular parameter negative. And this is a calculation that purports to show that. I don't go through the details of it, but in fact, this enabled some theorists back in the 1980s to predict, way before there were any indications from the precision electroweak data, that in order to make the origin of the potential unstable, we would need a relatively large top quark mass. Okay, so I've been talking about Higgs bosons and supersymmetry, and I mentioned the fact that supersymmetry actually predicts the mass of the Higgs boson, and it gets it more or less correct. So let me just say a couple of words about that. So it turns out that in supersymmetry you get what you might describe as double trouble, or double the enjoyment. You get two complex Higgs doublets. And then when you remove the degrees of freedom that are eaten to give masses to the W plus or minus and Z, you've got 5 physical Higgs bosons. The lightest of those at the tree level weighs less than mZ. And so back in the 1980s, experimentalists' lips were slavering because they thought at LEP we're going to be able to make this lighter than mZ Higgs particle. Unfortunately, our old friend, the top quark, went and screwed that, and we calculated the quantum corrections to the mass of the Higgs boson in about 1990 and realized that they would actually push the mass of the Higgs boson up. Not very far up, as I said, still less than 130 GeV. And this is a calculation of the lightest Higgs masses, the red line. The other lines are the masses of the other Higgs bosons. And the blue dashed line is the experimental value. And you can see that there's a large range of masses, a large range of parameters where the Higgs mass is consistent with the LHC measurement. There's actually 2 regions where it's consistent. There's also a little region over there on the left-hand side, but that's probably disfavored by experiment. Anyway, so this slide justifies the remark that I made earlier on that supersymmetry predicted successfully the mass of the Higgs boson. That's all well and good, but of course nobody has seen any trace of supersymmetry. We've only got constraints on it. And I'm a member of a collaboration called Mastercode, where we try to take all the present experimental constraints and evaluate their significance for the, if you like, fundamental constants of supersymmetric models. So there's electroweak precision observables, the things which I mentioned yesterday, which enabled us previously to predict the mass of the top quark and the Higgs boson. Do they have something to say about supersymmetric particle masses? There's all that flavor physics, which I haven't done justice to. There's the measurement of the Higgs mass. There's dark matter, the density of dark matter and its scattering rate. And of course, searches at the LHC. So I perhaps might mention just one experiment that maybe indicates a discrepancy with the standard model, and that is the measurement of the anomalous magnetic moment of the muon. I mentioned yesterday that the anomalous magnetic moment of the electron is a great success for field theory. Not so successful with the anomalous magnetic moment of the muon. And there's been some discussion that this might be due to, this discrepancy might be due to supersymmetry or some other low-scale physics, although I think that it's probably prudent to wait for a new experiment. The LHC has looked for supersymmetry in vain. And I think the purpose of this slide is really to convince you that the experiments have really tried very hard to look for supersymmetry. And there's lots of lines here corresponding to various different searches in various different modes. I'm not going to go through the details of it. So as I said, I'm in a collaboration which tries to put together all this information. This involves communicating between different languages, Fortran, C++, English, German, Italian, etc. If you looked at the most general supersymmetric model, it's got way too many parameters. You can't do a sensible analysis. You have to make some sort of judgment about how to simplify those parameters. So what can you do? So as I already mentioned, the minimal supersymmetric extension of the standard model has two Higgs doublets. This introduces over and above the standard model a couple of parameters. That's in the supersymmetric limit, but of course supersymmetry has to be broken, and that's where the additional 100 parameters that I mentioned come in. So what one conventionally does in analyzing the data is to make simplified assumptions, and the one which I'm going to be adopting on the next couple of slides is one in which one assumes that those supersymmetry breaking parameters are in fact universal, that all the scalars, the supersymmetric partners of the quarks and the leptons, have in some sense the same mass before renormalization, and similarly the unseen fermionic particles. This is a scan of the CMSSM parameter plane. Like I said, there's no evidence for supersymmetry anywhere, but the green stars represent best fit points. The red lines represent 68% confidence level regions. The blue lines are 95% confidence level regions. And that then enables you to give a likelihood function for example, here, the squark mass. And we would say, well, it pretty much has to weigh more than 1.5 TeV. It might weigh 2 TeV, or it might weigh 5 TeV. That's basically all we can say at the current time. If it's in that low mass region, then we're in luck because the LHC will be able to find it. But if it's not in that low mass region, then we're going to have to come back to our future circular collider. And this is a similar picture for the mass of the gluino. That's the supersymmetric partner of the gluon. And again, there's a low mass region which will be accessible with the LHC, and then there's a high mass region where we have to go back to our funding agencies cap in hand. That was, if you like, a relatively modest extension of the standard model, at least in terms of energies. I mean, I was talking about particles that might weigh only a few TeV. If we want to simplify the gauge structure of the theory, then I think the dominant idea on the market is so-called grand unification. And as is well known, this plays upon the fact that the fundamental gauge coupling constants are not constant. They vary. The strong coupling gets weaker. Here, these are all 1 over the inverses of the coupling strengths. So 1 over alpha gets bigger, and you could hope that you might have convergence between the SU3, SU2, and U1 couplings. As is well known, if you just do that within the standard model, those couplings don't quite meet. But if you do it with supersymmetry at a relatively low scale, then it works. And for many people, this is a nice piece of circumstantial hint in favor of both supersymmetry and grand unified theories. So if you just look at this picture here, you think, well, no, this is gee whiz. But I just wanted to spend one slide saying, well, it's not just gee whiz. Actually, there is a whole bunch of calculations that go into this. And fortunately, I won't show you the formulae that work at 3-loop order. But this has been looked into really quite carefully. So why should we believe any of this stuff? Well, if you have unification of the gauge couplings, then you have a specific prediction for the ratio of what I called yesterday G prime, the U1 coupling, and G2, the SU2 coupling. So you would get 3/5 in the limit where G1, G2, and G3 were all equal. At 1 loop, they get renormalized. So these parameters B here, these are the 1-loop renormalization coefficients. And these are those 1-loop coefficients without on the left and with supersymmetry on the right. So what you can do is you can take the measured value of sine squared theta, the measured value of the electroweak mixing angle, which I showed you yesterday, which is 0.23 blah, 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 blah. And you can ask yourself, what is the corresponding value of the B's? Actually, the relevant combination is what I call X there. And X has a value 1/7 in supersymmetric extension of the standard model. And X has a value 23 over 218 in the standard model. The data, you just put in the measured value of sine squared theta, correspond to X of 1 over 6.92 plus or minus 0.07. So that is, it's not a 1 per mil check of supersymmetric grand unification, but, it is an interesting hint. So in the simplest grand unified theories, the electromagnetic charge is embedded in a simple group. And because it's embedded, charge is quantized. If you look at any representation and you sum up the charges, they have to be equal to 0. I commented yesterday that if you write down the hypercharges in the standard model, they look like a bunch of random numbers. Of course, they're not really random, but random integers divided by 3 or 6. Well, those random numbers find a simple interpretation within a grand unified theory because, as I said, the electromagnetic charge is embedded in the simple group, charge is quantized. That remark is independent of the specific grand unified theory that you write down. The simplest one is SU5, and SU5 accommodates in a very simple way the fermions of a single generation, and this is how, for example, you would put the fermions of the first generation. Of course, you might wonder how you would explain the generation degree of freedom, and the answer, of course, is that you don't. As I've advertised previously, flavor is, to my mind, a completely unresolved issue. But at least you explain what previously looked like the somewhat random quantum numbers of the fundamental fermions. So I've talked about the fact that fundamental constants are not. They vary as a function of the energy scale. The same is also true for quark and lepton masses. You've got your propagator of a quark or a lepton, and depending on the momentum scale passing through that propagator, the effective mass parameter varies. So then you can ask yourself the same question as you asked for the gauge couplings. Is it possible that quark and leptons might be the same at some fundamental level? For example, in that SU5 model where I've got quarks and leptons in the same representation. In fact, in minimal SU5, the quarks and leptons in the same generation would have the same mass at the grand unification scale. Then you can calculate the renormalization. This was a calculation that we did in 1977. And for example, if you assume that the tau lepton and the bottom quark have the same mass, then you find the bottom quark is 2 to 5 times heavier. And this is actually a calculation that we did a few weeks before the bottom quark was discovered. So it's actually a successful pre, as opposed to post, diction of the bottom quark mass. Doesn't work for lighter quarks and leptons, but okay, those are the breaks. So I can't resist showing the abstract of another one of my papers. So this one we wrote in May 1977. You can see the received date of the journal there. And a few weeks later, the bottom quark was discovered. And so we said, well, you know, we actually predicted that. So we modified the proofs of our paper. And I wrote by hand that in the abstract, they should put in 2 to 5. And this was transcribed by the proof reader as 2,605. So this has the most spectacularly unsuccessful post-diction of the bottom mass. So when one is talking about cosmological parameters, as has been emphasized already, one has to distinguish between fundamental constants and what you might call environmental parameters. So examples of this might be the cosmological constant versus the Earth-Sun distance. So looking at what the cosmologists measure, which of these are candidates for fundamental constants that we should be able to relate to fundamental physics? Well, how about the baryon to photon ratio? I mean, that is something that we should be able to calculate a la Sakharov from fundamental physics constants. The dark matter density, if only we could discover supersymmetry, the fundamental constants of supersymmetry, the masses, etc., would enable us to calculate the dark matter density. The cosmological constant itself, surely, we should be able to consider that within the framework of fundamental physics. And of course, the very topical subject is cosmological density perturbations. And within a specific inflationary scenario, you could relate their magnitude, their tilt, and the tensor to scalar ratio to fundamental constants appearing in some effective potential for some inflaton field. So I imagine we're going to have more discussion of this, but just to recall to you that Copernicus would be horrified. We are not only made of a subdominant type of matter in the universe, but matter is in turn subdominant relative to dark energy. So one way of phrasing this is that we really are the scum on the surface of the universe. This plot you've seen 10 to the 5th times, and there's been a lot of activity over the last year or so, whether this is really evidence for what you might describe as a scalar in the sky, or possibly supersymmetry or supergravity. So I'm not going to question the inflationary paradigm. I think the point was made by Martin Rees yesterday that one could question the inflationary paradigm, but let me just take it seriously. Anyway, the position of that first peak in the microwave spectrum tells you the overall geometry of the universe. It tells you approximately the total density of stuff in the universe. And the peaks, their relative magnitude, tell us something about the density of ordinary matter and dark matter. And this is a compilation of the information that you get from the CMB in orange, which is combined here with information from other observations of structures, the baryon acoustic oscillations, and high redshift supernovae in blue. So there certainly is a lot of dark matter out there, a lot more dark matter than there is visible matter. And it's that dark matter, of course, that enables the minuscule perturbations seen by the CMB experiments, enables those perturbations to grow into galaxies, stars, Yumi and George Bush. And this picture I think you've also seen. This is just to show you that this model works extremely well describing structures on all scales. So I would claim that it is the job of us particle physicists to calculate those three red numbers on the left-hand side. The baryon to photon ratio should be related, for example, to CP violation somewhere in the fundamental theory. The dark matter should be related to some properties of some as yet undiscovered beyond the standard model. And dark energy, well, that's the biggest prize of all. Okay, so I said I'm going to be discussing fundamental constants in the context of inflation, more specifically in the context of slow roll inflation. So the magnitude of those perturbations, this is something which surely we should be able to calculate from first principles. We expected, and it has been determined, that the spectrum of those perturbations is almost flat. And the deviations from flatness in slow roll are related to parameters of the effective potential. So again, you can regard these as fundamental constants that we theoretical physicists should be able to feed through to the cosmologists. The universe has to expand sufficiently. The number of e-folds has to be about 50 or so. This maybe you could regard as being an environmental parameter, although it's of course related to the properties of the effective potential. So the main observables, in addition to the magnitude of the perturbations, are the scalar tilt and the tensor to scalar ratio, which is of course where the big excitement was yesterday. So this is the inflationary landscape, which was revealed to us by the Planck satellite. And these spots here on the screen are mainly monomial single field potentials like phi cubed, phi squared, phi to the 2/3. Those make predictions which were in some tension with the Planck data. The model which was not in any tension with the Planck data was the Starobinsky model, where you just put in an R squared term in your effective theory of gravity. But yesterday we got a somewhat different picture. So here I've adjusted a picture from bicep 2 to the same horizontal and vertical scales, and you can see that the focus attention has shifted up. The vertical axis is the tensor to scalar ratio R. The horizontal axis is the scalar tilt NS. So things look rather different, and whereas the day before yesterday you might have said, well, a phi squared potential looks rather sick. If you believe bicep 2, today you would say, well, that looks rather good. And whereas 2 days ago you might have said that Starobinsky looked in good health, today you might say, well, Starobinsky RIP. It's probably premature because there's obviously some tension between the bicep 2 and Planck data, and this needs to be resolved before one can, I think, draw any definitive conclusions. Anyway, I would say qualitatively the data are consistent with inflationary expectations, in particular because there was this tilt. 2 days ago there was an upper limit on tensor perturbations, and as you can see on this picture, that was a challenge for simple inflationary models except Starobinsky. But as I already emphasized, the picture has now become very confused, and maybe the day before yesterday's disfavored models have become the favored ones, and the day before yesterday's favored models have maybe become disfavored. So I've actually long taken the view that inflation cries out for supersymmetry. That's because inflation kind of looks like it wants an elementary scalar field, and in order to get the right magnitude of perturbations, that should have a relatively small mass and or a relatively small self-coupling, and those are things which are technically natural in the context of supersymmetry. So just as an example, 11 years ago, together with Rydal and Yanagida, we wrote down what we thought was rather a cute model where we've got a supersymmetric scalar, specifically the partner of a singlet neutrino, the sort of thing that you would have in a seesaw model of neutrino masses. And that has a very simple potential. It rolls down the potential, generates inflation. At the end of inflation, it generates the baryon symmetry. And until 2 days ago, I would have been downcast about that model because it seemed to be in tension with the Planck data. Just to situate this in the discussion of fundamental constants, that m sitting in there, that would be a candidate for fundamental constant, which hopefully would explain inflationary phenomenology. So here again is that overlay of bicep 2 on Planck, again adjusted so I get the same horizontal and vertical scale. And again you see that the phi squared model, such as this neutrino model, now fits the data quite well. So I'll skip through this slide because I'm running out of time, but needless to say, this is not the only scenario. There are other possible models that also fit the data. Maybe I sort of jumped ahead of myself a little bit, and these are the actual bicep 2 data that were released yesterday. So the signal that they see is over there on the left-hand side, and their value of the tensor to scalar ratio 0.2 is shown here over on the right-hand side. I think one perhaps shouldn't get too hung up on the details of the inflationary models. The primary significance of this experiment must be that finally we have detected quantum gravity radiation. Gravitational waves have been detected, and furthermore those gravitational waves were presumably generated by quantum effects in the very early universe. So I was in some Royal Society discussion a week or two back about good versus not so good Nobel Prizes. So for my last slide, this is actually a slight edit of a slide that I showed yesterday. Yesterday I wrote at the top here, we need more principles. And I thought about it a bit, and I decided actually what I meant was we need stronger principles. And if possible, we want fewer but stronger principles. So as I've emphasized, the gauge principle is fine as far as it goes, but there are many fundamental constants that it does not constrain. I think this audience seems to have decided to not speak the A word. I'm not sure about the M word. That seems to be still floating around, at least judging by Martin's talk yesterday. So I think that we theorists should shut up and think harder, and the experimentalists have shown already yesterday that they can give us plenty to think about. Thank you.